Connecting two ground rods together with a number 2 bare copper conductor and tying the grounding conductors from 2 panels and a copper water pipe to the rod separately is an acceptable practice. The National Electrical Code, or NEC, does not mandate that the 2 number 4 conductors from the panels and the number 4 conductor from the water pipe must connect to the number 2 conductor. In fact, the NEC allows for multiple grounding conductors to be connected to a single ground rod. Section 250.50 of the NEC states that where multiple grounding electrodes are used, they should be bonded together to form a single electrode system. This means the grounding conductors from the panels and the water pipe can connect to the number 2 copper conductor, but it is not a requirement. The reason it's not necessary to connect the grounding conductors from the panels and the water pipe to the number 2 copper conductor is that the number 2 copper conductor is already bonded to the ground rod. This establishes an effective ground connection for the grounding conductors from the panels and the water pipe. Connecting them to the number 2 copper conductor would not add any benefits. It may introduce a potentially hazardous connection. In the event of a fault, current could flow through the number 2 copper conductor and back into the grounding conductors from the panels and the water pipe. This could potentially damage the equipment or injure someone. The core concept here involves understanding the purpose of grounding systems and how they function to protect equipment and personnel. The grounding system provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices, such as circuit breakers or fuses, to operate and clear the fault. This protects the electrical system from damage and prevents electrical shock hazards. A grounding electrode system is the foundation of a proper grounding system. It typically consists of 1 or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes bonded together to create a low-resistance connection to the earth. The purpose of the grounding electrode system is to stabilize the voltage to ground and provide a path for fault current to flow back to the source. Ground rods are commonly used as grounding electrodes, especially when a metal underground water pipe is not available or is not suitable for use as a grounding electrode. Ground rod should be at least 8 feet long and should be driven into the ground until at least 8 feet of the rod is in contact with the soil. The NEC requires that if a single ground rod is used and it has a resistance to ground of more than 25 ohms, a second ground rod must be installed. The 2 ground rods must be spaced at least 6 feet apart. The grounding electrode conductor, or GEC, is used to connect the grounding electrode system to the equipment grounding system. The equipment grounding system is the network of conductive paths that connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. The GEC must be sized according to NEC Table 250.66, based on the size of the ungrounded conductors. The equipment grounding conductor, or EGC, is used to connect the non-current carrying metal parts of electrical equipment to the equipment grounding system. The EGC must be sized according to NEC Table 250.122, based on the size of the overcurrent protective device protecting the circuit. Bonding is the process of connecting the non-current carrying metal parts of electrical equipment together to create a low impedance path for fault current to flow back to the source. Bonding is essential for preventing electrical shock hazards and for ensuring that overcurrent protective devices will operate properly in the event of a fault. The NEC requires that all metal water piping systems that are likely to become energized must be bonded to the grounding electrode system. This is typically accomplished by connecting a bonding jumper from the water pipe to the grounding electrode conductor or to a nearby grounding electrode. When multiple grounding electrodes are used, they must be bonded together to form a single grounding electrode system. This is typically accomplished by connecting the grounding electrodes together with a bonding jumper. The bonding jumper must be sized according to NEC Table 250.66, based on the size of the largest ungrounded conductor. Grounding and bonding are essential for electrical safety. They help to protect equipment and personnel from electrical shock hazards and to ensure that overcurrent protective devices will operate properly in the event of a fault. Always follow the NEC and other applicable codes and standards when installing or maintaining electrical systems. In this specific scenario, the question revolves around connecting two ground rods with a number 2 bare copper conductor and then connecting the grounding conductors from two panels and a copper water pipe to these rods. It's important to understand that while connecting multiple grounding electrodes to form a single system is necessary, directly connecting all individual grounding conductors to each other may not be required and can potentially be detrimental. The number 2 bare copper conductor acts as a bonding jumper, connecting the two ground rods and ensuring they function as a single grounding electrode system. This satisfies the NEC requirement for bonding multiple grounding electrodes. The grounding conductors from the two panels and the copper water pipe each serve a specific purpose. The grounding conductors from the panels connect the equipment grounding system to the grounding electrode system, providing a path for fault current to return to the source. The connection to the copper water pipe serves to ground the water piping system, reducing the risk of electrical shock hazards. Each of these connections to the ground rods provides an independent path to ground. Forcing them all to connect to each other via a single point on the number 2 conductor can create a bottleneck and potentially increase impedance in the grounding path. This is contrary to the goal of providing a low impedance path for fault current. The NEC allows for multiple grounding conductors to be connected to a single grounding electrode. Therefore, connecting the grounding conductors from the panels and the water pipe directly to the ground rods separately is permissible and often preferable. The key takeaway is that while bonding multiple grounding electrodes together is essential, directly connecting all individual grounding conductors together is not always necessary and can potentially be detrimental. Each grounding conductor should have its own independent connection to the grounding electrode system to ensure a low impedance path to ground. Understanding the NEC requirements and the principles of grounding and bonding is crucial for ensuring electrical safety and protecting equipment and personnel. Furthermore, consider the practical implications of creating a single connection point for all grounding conductors. Firstly, it can be difficult to physically make a reliable connection with multiple conductors terminating at a single point, especially with larger gauge wires. Secondly, if one of the connections becomes loose or corroded, it can compromise the entire grounding system. Thirdly, troubleshooting becomes more complex as it's harder to isolate and identify the source of a problem. By maintaining separate connections to the ground rods, each grounding conductor has its own dedicated path to ground. This simplifies troubleshooting and reduces the risk of a single point of failure affecting the entire system. In addition to the NEC requirements, local codes and regulations may also apply. Always consult with a qualified electrical inspector to ensure that the grounding system meets all applicable requirements. In summary, connecting two ground rods with the number 2 bare copper conductor and then connecting the grounding conductors from two panels and a copper water pipe to the rods separately is generally acceptable and often preferable. The number 2 conductor bonds the ground rods, creating a single grounding electrode system. The separate connections of the grounding conductors provide independent paths to ground, ensuring a low impedance path for fault current. This approach complies with the NEC and promotes electrical safety. Always consult with a qualified electrician or electrical inspector to ensure that the grounding system meets all applicable codes and standards. The grounding electrode conductor size should be chosen based on the size of the service entrance conductors according to NEC Table 250.66. The grounding electrode conductor connects the neutral bus in the service panel to the grounding electrode system. This conductor provides a path for ground fault current to return to the source, allowing the overcurrent protection device to trip. The equipment grounding conductor runs with the circuit conductors and connects the non-current carrying metal parts of electrical equipment to the grounding system. This conductor provides a low impedance path for ground fault current to return to the source, protecting against electrical shock. Bonding jumpers are used to connect metal enclosures, raceways, and other metal parts to the grounding system. This ensures that all metal parts are at the same potential, reducing the risk of electrical shock. When installing ground rods, it's crucial to drive them deep enough into the earth to reach a low resistance connection to ground. The NEC requires that ground rods be driven at least 8 feet into the ground. In areas with high soil resistivity, It may be necessary to install multiple ground rods, or use other grounding methods to achieve a low resistance ground. The water pipe electrode is another common type of grounding electrode. If a metal underground water pipe is available, it can be used as part of the grounding electrode system. The water pipe must be in direct contact with the earth for at least 10 feet to be considered an effective grounding electrode. When using a water pipe as a grounding electrode, it's important to bond around any insulated joints or sections of non-conductive pipe. This ensures that the entire water piping system is effectively grounded. Concrete encased electrodes, also known as UFO grounds, are another type of grounding electrode. These electrodes consist of a length of bare copper conductor encased in concrete. UFO grounds are typically installed in the footings or foundations of buildings. They provide a very low resistance connection to ground and are often used in areas with high soil resistivity. Grounding and bonding are essential for electrical safety. By providing a low impedance path for ground fault current, they help to protect against electrical shock and prevent damage to electrical equipment. It's important to understand the NEC requirements for grounding and bonding and to follow them carefully when installing or maintaining electrical systems. The purpose of the grounding electrode system is to provide a stable reference point for voltage and to provide a path for fault current to flow back to the source. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, water pipes, or concrete encased electrodes connected together to form a single system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors according to NEC Table 250.66. The grounding electrode conductor connects the neutral bus in the service panel to the grounding electrode system. The equipment grounding conductor is run with the circuit conductors and connects the non-current carrying metal parts of electrical equipment to the grounding system. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit, according to NEC Table 250.122. Bonding is the process of connecting metal enclosures, raceways, and other metal parts together to create a low impedance path for fault current. Bonding jumpers are used to connect these metal parts to the grounding system. Grounding and bonding are essential for electrical safety. They help to protect against electrical shock and prevent damage to electrical equipment. Understanding the NEC requirements for grounding and bonding is crucial for ensuring the safety of electrical systems. When connecting grounding conductors to ground rods, it is important to use appropriate connectors that are listed for direct burial. These connectors are designed to withstand the corrosive effects of soil and moisture and will ensure a reliable connection. It is also important to properly torque the connectors to the manufacturer's specifications to ensure a good electrical connection. Improperly torqued connectors can lead to loose connections, which can increase resistance and reduce the effectiveness of the grounding system. When installing ground rods, it is important to choose a location that is free from underground utilities and other obstructions. Before driving ground rods, it is advisable to contact the local utility companies to locate any underground utilities in the area. Driving a ground rod into an underground utility line can be extremely dangerous and can result in serious injury or property damage. In areas with rocky soil, it may be difficult to drive ground rods to the required depth. In these cases, it may be necessary to use alternative grounding methods, such as installing multiple ground rods or using a ground plate. A ground plate is a flat metal plate that is buried in the ground and connected to the grounding system. Ground plates provide a larger surface area than ground rods and can be more effective in areas with rocky soil. When using a ground plate, it is important to ensure that it is buried deep enough to be in contact with moist soil. The depth will depend on the local soil conditions and climate. Another important consideration is the material of the ground rods and connectors. Copper ground rods are commonly used, but they can corrode over time, especially in acidic soils. Stainless steel ground rods are more resistant to corrosion, but they are also more expensive. The connectors used to connect the grounding conductors to the ground rods should also be made of a corrosion-resistant material such as copper or stainless steel. Regularly inspect the grounding system to ensure that it is in good condition. Check the ground rods and connectors for signs of corrosion and replace any damaged components. Also, test the resistance to ground to ensure that it is within acceptable limits. A high resistance to ground indicates a problem with the grounding system that needs to be addressed.